yeah, I spent most of my career in high performance computing with a linear software, which was recently acquired by ARM at the start of this year. And now, as part of ARM, our team remains unchanged as the core of ARM's HPC tools division now. And it's been very interesting because ARM doesn't actually sell hardware. Rather, they operate as kind of stewards of an ecosystem of hardware and software vendors. And one of the ways that we keep the hardware vendors honest is by providing high-quality cross-platform tools to allow users to select the hardware that matches their needs and to increase choice. So this matches very well our message as cross-platform tools vendors as linear in the first place. And I'm really happy to be here sort of representing the open ecosystem. So Knights Landing, I think, is a particularly interesting platform because, I mean, we can see in the pipeline coming down, there's really three significant architectural changes that everybody's going to see. One is having many cores. With the end of single core scaling, all future chips have more cores per socket. Several providers are looking at lots and lots of little cores instead of a few big ones, or even a hybrid model of large and small cores in a single socket. And as I think we'll see, and some of us have already seen, this brings really interesting challenges, kind of above and beyond traditional scaling. Another one is the prevalence of very wide vectors, 512 bits today. We have research projects looking at 1,000 or 2,000 bit vectors. And I think the success of GPU workloads has shown you can benefit from very wide vectorization if you can keep these units filled. And keeping them filled is always the challenge in making the most out of these. And finally, high bandwidth memory, or rather the deepening of the memory hierarchy. In the future, we'll also see non-volatile memory playing a much larger part here. But here we're getting more and more layers in the memory hierarchy than we've had previously, and it sort of blurs these somewhat artificial lines between the memory and the storage subsystems. And will all memory access be treated as I/O from the CPU's perspective, or all I/O as memory accesses? So it's going to be an interesting future. And the cool thing about Knights Landing is it hits us with three of these all at once. It can be kind of a bit of a shock to the system. So this survival guide and our time together today is, I just hope to help you make the most of the current systems that are out there, but also to prepare your code well for the future, because none of these technologies are going away. So in preparation for this talk, I asked some performance experts, all of whom, like you, are much smarter than I am, and who've been working on Knights Landing, for their advice, so that I could sort of pass it on to you and pass it off as my own. So the first piece of advice I got was give up before you start. Very, very helpful. Now that was followed up by the sage advice, the compiler giveth and the compiler taketh away. I heard that less is more, which sounds like wisdom, but it was followed quickly by the proviso that sometimes more is less. And one guy just huddled in the corner and muttered that performance counters are tricksy little hobbitses, and went off talking about his precious. So I'm going to try my best to make a talk out of these and to help you feel that you've extracted some wisdom from the inanity of this world that we live in. So giving up before you start, it's always good to start with a crowd pleaser. There's a lot said about the Knights Landing. I would suggest it's neither better nor worse than the Xeon, so much as it is different. Just because it has the x86 instruction set doesn't mean it looks anything like the sort of system that you're used to or your applications would normally run on. Different applications benefit to very different degrees. So here we've got the NASA parallel benchmarks, which I'm sure many of you are familiar with. If anybody is not, these are well-optimized kernels that look at different kinds of computation that are in some ways representative of different scientific workloads. And we can see, compared to even the old Haswell cores, in some cases, like the LU benchmark, you're getting hardly any speed up on the Knights Landing at all. In other cases, 3 or 4x. This kind of underscores the point that performance portability as such is today a dream. It's not the reality of today. So for your code, it's going to be important to know which benchmark is my code most similar to. Most sites have a preferred benchmark or range of benchmark suites they use for kind of characterizing systems. I do recommend getting the numbers from the support staff for an on-site Xeon system and the nice landing system, so you can see yourself how these compare, and just find the one that best matches your application and use that as a guide. And if you have many applications or several, pick and choose. Night's Landing might not be the right architecture to go with first for all of them. You might have to start with something that looks like it's going to be a bit easier. It's quite possible, as in the case of the Ali application here, that you don't get speed up at all. That is also a possible outcome. Every now and again in this talk, I've linked some recommended reading. These are a handful of sites that I found particularly useful in the past, and I do like to refer people to. All the links will also be in the final slide at the end, so you don't need to take too many notes. When you're characterizing your own application, do use a real workload. This idea of extracting microkernels is fine when you're doing single core optimizations, and you will probably have to do that. But don't use it to try and characterize how your application looks. In particular, things like networking bandwidth or even I/O bandwidth can cause issues. So this is part of a paper that was published from the Corey system, which is a very large Night's Landing system, where they discovered that their Night's Landing nodes were delivering much, much lower I/O bandwidth than their Haswell nodes. And they really dug deep into this to try and figure out what was going on and get to the bottom of it. But as an application developer, when you have something like this, it doesn't really matter if it's a system configuration issue or if there's some underlying reason why this has to be the case. Fundamentally, you need to be aware and to know that if your application relies on a certain amount of I/O bandwidth, that it might be starved of that on this other system. So look at a real workload that will have realistic I/O sizes and not just a small test workload on a single node. And it's not always just about system bandwidth either. So one code that I saw that had been ported to a many-core system, it was using extremely large human-readable input files. I'm on the Xeon for generations of Xeons, this would be fine. But on the many-core machine, a single weak core wasn't actually fast enough at string-to-float parsing to max out the file system. So reading the input file became this sort of significant compute bottleneck that nobody had expected. And that had never been seen before on this fat node architecture. So just another bit of motivation to always use a profiler on the old architecture, and then again on the new systems, you can see what's changed because things will always surprise you. What else might be a reason for you to give up before you start? If your code does not scale, scaling to 64 procs on a single node is fine. Whether you're using MPI or OpenMP, it actually doesn't really matter. If we look at the kind of the black horizontal lines on these charts, so the left-hand one is the scaling of the NASA parallel benchmark suites using pure MPI implementations, and the right is pure OpenMP implementations. On a case-for-case basis, there are some differences here, and that is a log scale of speedup. But ultimately, if you're using all of the 64 physical processors, that's probably 9 times out of 10, that's all you're going to get. So as a scalability target, you need to be looking at least 64 cores per node. You'll be looking at many nodes. So if your code scales well, you're going to have a good time. But if thousands of cores is already a challenge for your scalability, then again, maybe a many-core architecture is going to be a problem for that. There is this kind of myth around the Xeon Phi in particular that you have to use MPI on the physical cores and OpenMP on the hyperthreads, or that pure MPI applications can't scale on the Night's Landing. And I don't think that's true. To a certain extent, it was true of Night's Corner. But on Night's Landing, the results I've seen, like the ones for GrowMax here, suggest that most can scale to a full node of 64 processors, even with pure MPI. And to get 90% of the performance, that will probably be fine. So do at least try this before doing a lot of work that maybe you don't need to. The important thing is to scale, not how you scale. So in terms of giving up early, just evaluate your code honestly for its suitability for a system like this. And there's kind of a range of different things you need to look at. It's a very holistic idea. So yes, you need to characterize the performance both in compute, but also in the time you spend in MPI or in IO. You should clearly look at the scalability, not in terms of, oh, I have to make it a hybrid code, or I have to make my OpenMP scale to more than 4 threads per processor, but just at the base level of expecting to have at least 64 cores per node that you need to make use of, and each core will not be anywhere near the speed of a fat core. Vectorization is a huge topic, and there will be many opportunities to go into as much detail as you want about vectorizing your code. In terms of choosing whether this code is the right one to put onto a Knights Landing machine and to do it today, if you're not already using AVX or AVX2 instructions, you might have a lot of work ahead of you. It's not trivial. The compiler's not magic. You need to look at things like alignment. Maybe your data accesses aren't actually wide enough to fill 512 bits in a loop. So seek expert assistance in that situation, or maybe just choose a different code to put on Knights Landing first, or choose a different machine. But making sure that your hot loops are vectorized will be very important, and that can go as far as reordering data structures and things that are generally a lot of painful work. However, that said, any time you spend doing this is never wasted. It will make your code run a lot better on a Xeon. It'll make your code run a lot better if you ever port it to a GPU or in future architectures. As we said, very wide vectors are not going away. They're a very energy efficient way of getting to higher performance. Particularly in terms of the Knights Landing, memory bandwidth is definitely significantly better with high bandwidth memory. Latency is kind of tricky. Latency is not necessarily going to be improved, particularly if you're running in cache mode. That can add extra latency to the DRAM. So typical things you want to care about is how large your working set is. What does access patterns look like? Even to know, are you running in flat mode or cache mode? Do you get the choice on the system you're running on? So there's a huge amount to take in evaluating code for suitability. One of the things that we tried to do in the past to help with this, we've used a tool called performance reports that gives like a one-page HTML summary of your code that you can use on an application by application basis. It looks something like this. And you just run it on sort of an unmodified binary. And it will spit out the high-level overview. So you can get things like this, characterization of CPU, MPI, IO. It won't dive right deep into the performance counters. If you're using a linear map, for example, you can see all of these metrics over time as well, or even over lines of source code. So you can look into your hot loop and see what percentage of time is spent in vector instructions versus memory instructions and so on. There are plenty of other open source tools that you can use. There are other commercial tools that you can use. These are the ones that I'm familiar with, but I do recommend using some kind of tool because, as I said, when you go to an architecture that looks significantly different, you will find bottlenecks in unusual places. And you need some kind of tool that will give you a good overview to learn about the things you don't know yet, the problems you didn't think you were going to have. And no tool, neither ours nor anybody else's, will take you all of the way there. The aim is to get most of the way there as quickly as possible. So you can decide yourself whether you're going to give up early or whether you have something that's worth persisting with. I talked a little bit about vectorization, and vectorization is not very easy. One of the ways that people try to make vectorization simpler is with auto-vectorizing compilers. They are not magic. having looked at compiler source code for a while and worked with compiler authors, optimizers they're a conflicting list of heuristics. There's plenty of trade-offs to be made. It is definitely not magic. So at the very least, make your compiler tell you what it's doing and what it didn't do. The reports you'll get out of ICC, GCC, and similar compilers are extremely long. Know where your hot loops are. Use a profiler to find them if you have to. And there's literally grep the reports for these. Sometimes you'll be very surprised. And the advice, if you can interpret it, and it is something of an art interpreting compiler vectorization advice, it's even worse than C++ error messages. But if you can interpret it, then the advice is usually helpful in helping to vectorize loops that otherwise could not be. The problem with this is when a compiler does auto-vectorize a loop, you have no strong guarantees that it will always do that when you make changes. And it's extremely easy for relatively minor changes by some grad student 6 months down the line working on something unrelated to accidentally flip one of these heuristics in the compiler scenario. It'll decide not to vectorize this loop after all. And you won't get any warnings printed out, you won't get any errors. All that'll happen is that your code, when you do another production run, will be like 8 times slower, or perhaps only 1.1 times slower. So I strongly recommend using continuous integration and regression testing anyway for correctness, just as part of good software practice. I do recommend using them for performance. That is more challenging because we all know that systems have a certain level of noise in performance. But certainly checking things like compiler vectorization, you can literally check the output of the compiler vectorization report as a test in your system. And then every time a build goes through, it can be checking that output for you and saying, yes, these loops are still vectorized, and no fewer loops are vectorized than last time. Even for critical loops, you could call them out by name. For our part, in trying to make it easier for people to adopt these tools and these working practices, we've made sure that map and performance reports will do JSON exports, so you can feed any of the metrics that you see in these tools into things like Jenkins or Bamboo, and get nice little charts of how your memory usage changes or your vectorization percentage time changes over different revisions and so on. And you can go back and find where the regression was. Setting all of this up can be a bit of a pain. Some sites have teams of people setting this stuff up, but it's not in comparison to the actual rocket science that many people who might be doing. This is not rocket science. It's just Python scripts and get everything's working right. Spend some time getting it going once, and then a little bit of time every week keeping it going, probably. But it pays for itself in terms of locking in the benefits that you've worked for and not letting them get taken away from you by the vagaries of a compiler upgrade. So our third piece of advice is that when you're trying to scale the nice landing, less is more, more or less. And this is really about trying to use the weird layout that the nice landing has. So rather than just having a couple of cores per socket, you have tiles. And within each tile, you've got multiple cores. Each core, you've got multiple hyperthreads. Affinity is super important. Not just for the usual reasons of not having threads dumping on each other in cache locality and so on, but if we have a look at the layout, you have different numbers of hops out to the network, depending on which tile you're on, different number of hops out to the memory, as well as between cores. So there is clearly benefits to be had from figuring all of this out. And again, this is complex enough for a tutorial on its own. Helen He from NERSC has done a very nice one, which I recommend. It's just worth reading through. There are some basic tips like having one logical core per MPI task and using KMP affinity equals verbose just to make at least the Intel MPI tell you what the hell it's doing to start with. But as you can see, even if you're not using the hyperthreads, different process layouts can have a massive 2x impact. You can see on the right-hand graph here. And when you are using them all, then it's still important. So on the night landing, there's no point at which you can throw your hands in the air and say, affinity, whatever the standard is. It will vary from application to application. It will vary sometimes from data set to data set. So do spend some time, pay attention to it. Performance counter interpretation is its own kind of black magic. We're somewhat fortunate, I think, that there are a wide range of performance counters available on modern CPUs. This was not always the case. And so it's really an embarrassment of riches in terms of we have hundreds and hundreds and hundreds of different performance counters. You get to choose 8 or fewer in many cases that you can measure on any given run, and no, not those ones. So the question is always, how do I get this information? What information do I want to collect? And not just how can I trust it, but how can I interpret this in a way that isn't shooting myself in the foot? For the night's landing in particular, so the nice thing about the night's landing being an x86 architecture is most of the performance counters that you would get on a Xeon you still have. You can interpret them generally in similar ways. Things like CPI, things like cache hits, cache misses. The most interesting ones, I think, are all about the high bandwidth memory. So if you're using the high bandwidth memory and it's configured in cache mode, what you want to know is, how well is this cache being used? And indeed, there are counters, little Miss Clean, little Miss Dirty here, that you can configure to actually measure your MCDRAM bandwidth. And that's a very, very useful thing to know when you're trying to figure out, should I actually be moving to flat mode? Should I be manually managing this memory access? When you are in flat mode, even more interestingly, the MCDRAM appears as a second NUMA node. And when it's a NUMA node, we can read information about how much memory has been allocated in any given NUMA node. So one of the things you can do is you can create your own counters that will literally graph the amount of memory allocations you've made in MCDRAM, which in this chart here is our NUMA node 1, versus DRAM as NUMA node 0. And like that, you can track over the lifetime of your application how much memory, which phases of the application are really using that MCDRAM effectively, which ones are not, which ones are overflowing it. Making good use of this is going to be essential to getting good performance from the Xeon Phi. And again, this is not a one-off architecture. So future Xeons will have MCDRAM. Other future architectures will have this sort of high bandwidth memory as well. So this is it's not just a challenge, it's your opportunity to kind of get ahead of the curve and get your code ready for this. In terms of our tools, so with MAP, it doesn't come with these counters out of the box. You can use add your own custom metrics. We did this a few lines of code, and there's a tar file you can download, which will support this. And we have support teams who are working on sort of packaging that a bit more nicely over the coming weeks. So that's been a whirlwind tour of these 4 areas of main advice. I think what it would be useful to do would be to talk just a little bit about experiences that people here have had so far. I'd love to know if anybody on the call has actually already ported their code to the Xeon Phi, particularly to the night's landing rather than night's corner, and what experience has been. And if there's any advice that you would like to share, or things that you would agree with here or disagree with here. So now it's open to the floor. Has anybody here actually already ported something to the night's landing? Nobody.
How about you, Jean? Some of you I know must have been part of the Theta Early Science program.
So do we have a lot of people who are currently porting code to the nice landing, or is this more general interest and or rabbit in the headlights fear?
I'm sorry, Mark, I didn't catch the last part of what you said. Could you repeat?
Yes, open question to the room. Are we a channel full of people who actually have not ported to the nice landing yet and know that it has to be done, or are just curious and wondering if they can get good benefits from this?
I have ported my application to the KNL. I'm Jean
How
Torres.
is that?
Yeah, I mean, I have tried in the Stampede supercomputer. I've gotten some gains, but I'm in the lookout for the best tool available, either on Stampede or Theta, for checking the performance and see the bottlenecks. What's different? Where can I get improvements? I've used the HPC toolkit, and I have been able to clear some bottlenecks, but I was wondering if what are the best tools in Theta to test potential bottlenecks and get performance gains.
I mean, maybe Ray, do you know?
Well, I mean, I think the way to look at this is that it's a multi-pronged approach, and that you might get different insights from different tools. So HPC Toolkit is certainly a good place to start, and a linear map might be. Linear map is certainly another tool to try, and each of them has some pros and cons. So Mark, maybe this is you could say a few words about where you would place map and performance reports in your strategy.
Yeah, absolutely. So the strategy with certainly map and also performance reports was to make it easy to get an overall feeling for how much time do I spend on each line of code, and why. So there are not very many sort of strange charts to interpret, or sort of super powerful visualizations of lots of things going on at once. They're designed to have a very low runtime overhead. They can take extra time at the end of the job, but it shouldn't slow down the execution of the job itself, meaning you can run it at fairly good scales to look at things like, which lines of code are spending time in I/O and not just the CPU-centric view, or MPI. And they try very hard to give these fairly cross-platform views of the time spent in the CPU instructions, rather than using performance counters directly, so that you can compare two systems or indeed two different CPU generations. It's very much, it's a tool that I think is very much aware of its own limitations. So it will never do performance tracing, for example. The idea is that you'll get 10, 20, 30 megabyte output files, not 20, 30 gigabyte output files. So it should be a good way to do this early characterization and to look at particular areas of source code to know where the time is being spent, to find these surprises, to confirm your own beliefs about the performance of the code. What it will not do is map will tell you, which loop you're spending your most time in, which lines of code. It'll say whether it's well vectorized or not. It'll tell you whether you have spending your time in memory, but then it won't go the next steps and say, well, this is definitely memory latency, and that's memory bandwidth to level 2 cache, and there's pipeline stalls here, and you're missing there. At that level, we tend to say at that point you need a performance specialist who will be familiar using something like Tau, or certain modes of Scholastica or Intel VTune to dive much more deeply into this one specific area of the code once Matt's highlighted it. So I think those are probably the strengths and the limitations of a tool like that.
So you would use this for a first look to get an overview, and then you might want to move on to a more complex tool such as HPC Toolkit or Tau after you kind of have an idea of what you're looking for.
Yeah, absolutely. The aim is to be kind of like a gateway drug to kind of get people hooked on performance profiling and then lead them on to the hard stuff when they've got a motivation to do it. Because there's so many different, I mean, there's huge, and this is the strength, I think, of our industry. And the interesting part of our community is there's so many smart people doing really deep and interesting tools. And one of the things I'd like to do more of, I think, and we've chatted with some of the tool writers over this, is finding ways to get these tools to communicate better, to hand people off from one tool to the next, to make that kind of whole ecosystem of tools play a bit more nicely together. Because as you say, there's never going to be a one tool fits all here.
So I think it's definitely the case that when you're not familiar with any of them, they all seem somewhat daunting, so that it is a good idea to pick something simple to try, and then like you say, you kind of get hooked into you're familiar with it, and now you know where you have the ability to go farther.
Right, and when you have a favorite tool and you build up that familiarity over years, you know its strengths, you know its weaknesses, you know when not to use it, you know how not to shoot yourself in the foot. I think what I try very hard to do with map and performance reports is to give an option where they will not let you shoot yourself in the foot by default. So you'll get at least you should get some benefit every time you run it. Yeah.
I have become familiar in the past with Tau and HPC Toolkit. But I have been trying to use HPC Toolkit on Theta, but I haven't been successful. There are some errors with linking, so I don't know if you can let me know if it's available.
Well, we'd have to pursue that offline since that's a completely different topic. But yeah, certainly we can look into it, and maybe having John Mellercrummy give a one of these developer sessions would be of interest. Would be a natural follow-up.
I see. But in principle, are all of these profilers available in Theta? All linear map, Tau.
Yeah, Tau and the linear map are both available currently. Yeah. Mm-hmm.
Okay.
I don't think that performance reports is part of the basic package, Mark. Is that separately licensed?
Yeah, that's a separate thing. But if you already have map, then you can get access to the same information. It's just packaged differently.
Yeah.
Thanks.
Yeah, performance reports is really kind of a lighter weight map for people who don't want to learn how to use a GUI, which certainly has its own benefits. But you can get the same data from map.
Yeah, I've had more experience using map myself than performance reports. David used it as David did a demo. I believe last year at PESC, but we haven't had it. We haven't had it available except for that. So, does anyone else have would be wonderful if any of the other participants could share what their situation is. With respect to debugging or performance analysis on Theta so far. And
especially if anybody's had a really good experience where it just just recompile network and it was speed up. That would also be great.
Even if you've tried something and you just don't know what to do, is a good topic to discuss about where to go, how to get started, and where to go. So, Mark, you touched on looking at the memory hierarchy. For someone who is not sure whether they can even benefit from using the MCD RAM and choosing what mode to be in, would you have any advice about just how to approach it?
Yeah.
How to kind of look at your program and say, yeah, maybe cache mode is not the best for this part of my code, and I should try doing it in flat mode or something like that.
So I would say 90% of the time, cache mode will be fine until you're trying to squeeze out every last bit of performance. I mean, there are, as we mentioned, latency is one of them. There are some pitfalls. There are some places you can get tripped up. But by and large, most of the time, cache mode will give you the best performance, or close to the best performance, right? You can always squeeze more out by doing things manually. In terms of understanding when that should maybe change, or whether I'm leaving performance on the table by doing that, there's a couple of places I'd go. I mean, one of them is, as I alluded to before, if you can look at the memory usage graph and say, yes, this is the size of my working set. If you know that fits inside the cache, then it's probably doing all of your work for you. It's when you're working on a much larger working set than that, and you have things like you may have bad cache access patterns through the MCD RAM to the DRAM, right? That sort of thing, as I mentioned here, you might find out through the MCD RAM calculation.
So are you referring to hitting the, because it's a direct map and it may not be, you may be colliding, that kind of thing?
Well, yes, and one of the issues, particularly if you're using more OpenMP threads, because in cache mode, the MCDRAM acts as a last level of cache, the night landing has to maintain cache coherency between all the different processes. Just the extra overhead of this can give you additional latency, which is, it's a price you have to pay for convenience. But yeah, with using flat mode, you can get around that. But again, I find memory latency is extremely difficult. Best thing you can do is pull out the various performance counters and give yourself some histograms, right? And the question is always, is this normal? It could be better, could be worse. With the night landing in particular, it is sometimes been illuminating to run the same code in cached mode and in flat mode without using any MCDRAM at all, just so you can see the difference between, because in the histograms you see fairly clearly where you're hitting DRAM and where you're hitting MCDRAM. And just to see the difference of those populations and how that affects your application will give you some ideas of what might be left on the table. But I think this is still one of the great challenges for tool writers, and also to some extent the architecture teams, in exposing what on earth is going on with these deeper memory hierarchies. It'll be the same story again with non-volatile RAM in terms of the storage hierarchy. The deeper these things get, the harder they are to interpret from the perspective of your application. The more magic there is going on and the more potential failure modes that you otherwise wouldn't necessarily be aware of. Yeah. And of course, if
yes,
you know...
all of these systems are getting, by by necessity more complicated. It's a monotonic trend. So
yeah.
I think until they become self-aware and solve the problems themselves, then we will just have to figure it out.
Yeah, until they figure out that we're the problem. Yeah. That off at source. One possibility is run your code in flat mode. In a tool like Map or VTune, I think, can do fairly similar things. Look at the statistics for your hot loops. Look at the amount of time spent in memory accesses. It would be lovely if we could show latency versus bandwidth here. We can't without adding extra overhead to the code, so we don't. But certainly in hot loops that are memory bound in flat mode, look at the data structures, see if you can allocate those data structures into your MCDRAM first. Your hottest loop that spends most time in memory access, you can break it down and see where you're making the most out of this. So rather than the top-down mode of use it all as cache and then see where the failures are, you can start with flat and then see you can get extra performance by putting the cache in just for the data structures that are accessed most frequently. I know of teams that have done that approach. I think it's more work, but by the end of it, you know exactly what you're doing and what your code is doing, and that makes these potential failure modes much easier to diagnose when you've specifically chosen what you want to go where. And there's the beauty of hybrid modes. You have some cache and some flat. And, I don't recommend that. It'd be interesting to hear if anybody on the call actually does characterize their application in terms of, are there representative benchmark workloads that I know are already well optimized for different systems that I can compare it to? Has anyone on the call done this? Is this regular day-to-day work for you guys, or is this would this be something unusual, an extra workload you wouldn't already do?
Well, I know that, for system comparison purposes, we've done this, sort of as part of the acceptance and so forth, but I don't know for, other than the several projects, some of the benchmark kernels that we used came from, projects, real projects. That's why we chose them to be realistic, even though they by necessity had to be just kernels. But in general, I don't know if your typical project has taken the effort to strip something down and compare it between platforms.
Yeah, and I do think that's where characterizing your code and some benchmarks on the same system, just so you have a feeling for which of these other codes or benchmark codes where someone has done that work for you are the most similar. Almost like nearest neighbors matching machine learning will give you a good feeling for whether you might have a good candidate here for running on system A or system B. Because most code teams have a choice of systems to run on these days. Just matter of making sure you're doing the most efficient choice.
I think you had a very good point at the beginning about you were talking about that case study of the application where a single core didn't have enough horsepower to process the input file, and the general idea that I've seen this happen a lot, that when you arrive on a new system, something is not behaving the way you expect it, but you unconsciously have assumptions about how things were working on previous platforms that, you never had a reason to specifically investigate them, but it wasn't causing a problem because it wasn't causing a problem. But moving to the new platform really is just exposing something that was a problem before, but you just got away with it. So that does happen. And it's actually pretty common.
Yeah, things that were costing you 10 or 20% before for years that you didn't notice. You don't notice until it costs you 100%.
Yeah, exactly. And it's a very common thing when we are working with users that, there's some problem. It may be an outright error. It may not have come to a head as a performance issue, but it may have actually come to a head as manifesting as an error. But in fact, it was something that, existed previously, but it just wasn't known.
Yeah, a classic one we saw scaling up the code on the UK supercomputer was in the part of the domain decomposition. It was possible to get integer overflow. And of course, that only happened when they moved to 50, 60,000 cores. Suddenly the code was just segmentation fault. And again, that would happen to you on a Knights Landing if you have more cores, and it's nothing to do with Knights Landing at all. That problem was always there. It's just waiting.
The programmers for the Ariane had a little issue with integer, or at least with data type overflow. Right, that was caused one of the launch explosions when I think it was something like a 16-bit number rolled over. It should have been 32 or 32 versus 64 or something like that. Net result is a few billion going up in smoke. Luckily, our accidents are only core dumps.
Yeah. I'm glad I've never done that much damage to anything.